G'day, it's Prezzo here, back in the shop, and today's video is about making a metering valve for a home shop blasting cabinet. You've probably seen lots of videos about the Harbor Freight Sandblaster or Media Blaster, and you've probably looked at all of the upgrades that they recommend you do after you buy one of these things. And it's a bit of an indictment on the manufacturer, really, that no sooner do you buy it than you need to do a whole bunch of remedial work to actually make it operate effectively. Now, the one that I bought, I went through and did most of the upgrades. I improved the lighting, I sealed the lower section of the cabinet. What else did I do? I put a liner on the inside of the door so the media wouldn't fill up the little holes in the pockets in the door. I made a trolley or caster base so we can wheel it around the shop. And to me, the most important upgrade was to make sure that I could get a continuous flow of, and I'm going to use garnet, but I need to get a continuous flow of garnet to the gun. Now, the device that they supply with the blast cabinet, you might as well throw it in the bin as soon as you get it. It's not effective, it doesn't work. Now, there is an upgrade that you can purchase which includes a foot pedal and a thing called a metering valve. Now, I considered buying one of these, but unfortunately when you live in Australia, US manufacturers don't really want to ship to Australia. The cost, we pay 30% just on the value of our dollar for whatever it's worth, and then you've got the shipping charges and tax and everything else, and it just becomes impossible. So what I considered doing was replicating the operation of this metering valve based on what I understand it's supposed to do. And essentially what you want to do is to take the media from the hopper, take it through a right angle bend here, and then at this point here we're going to add air to the mixture. And what that does is it fluidizes the flow of media so it will pass through the clear plastic tube to the actual blast gun more freely. Now, in my last video I made this casting and I did it using a 3D printed core box, and I used an epoxy resin and sand mixture to make the core, and that was a resounding success. I ended up with a casting that's hollow all the way through, plus a tapered section inside here. So what I'm going to do today is to do all the machining on this and see if we can get it working. But before we do that, let's have a look at a diagram which I hope will explain how these metering valves operate. Okay, well I could have done some fancy CGI animation, but I thought, hey, what the hell, let's do it old school. So this is a diagram which I hope explains how this metering valve works. Now, if you've got one of these Harbor Freight blast cabinets or a Hare and Forbes one, they're the same, you'll know that this is the bottom of the hopper. There's a flap at the bottom here which can be opened to drain the media out. Now, the modification that I've seen in kit form, and the one that I'm trying to replicate here, allows you to drill a hole in the bottom of that flap there, put a coupling in place, and this aluminium casting, which you've already seen, has a path going straight through and blocked off by a cap at this end. You can undo the cap and drain the media out of the hopper if you need to. Now, this section here, this tapered section, diverts the flow of the blast media to a coupling at this end, which is connected to a clear plastic tube. And it's tapered. Now, I'm guessing that the reason we're having this taper here is to create a venturi effect. Now, the sand itself is, if it's not doing anything, if it's just sitting there, it's like a solid. But when it's starting to be drawn along by the vacuum created by this gun, it becomes like a fluid. Now, as any fluid passes through a venturi, its velocity increases. When the velocity increases, the pressure drops. Now, the pressure drop allows air to be drawn through this variable metering valve, and the air then mixes with the flow of the blast media. I'll call it sand because it's easier. So now we have a mixture of sand and air passing through the venturi, and because that has a lower density, it's mixed with air, the theory is it's easier to be drawn up by the hose and into the blast gun itself. Now, all of this is based purely on speculation and my very, very limited knowledge of fluid dynamics, and also from me studying a few fairly low resolution images. Now, if I've got it wrong, feel free to shoot me down in the comments section, but that's my take on what's happening here. So I'm going to go ahead and make this and fit it to the cabinet and see if it works. One of the first things I have to do here is to make a plug to go in this end here. This will be where the media is drained out if you want to change over what's inside the Sandblaster. Now, I went down to the hardware store and I bought one of these little threaded plugs thinking that would be ideal. Turns out that this is 24.5 millimeters diameter. The drill size for this is not going to work, so that's scrap. So I'll need to make a plug from scratch. Now I've got some brass here which was left over from a casting job that I did, and surprisingly this machine's beautifully. So we're going to cut a thread, a male thread on this. It's going to be 1/8" UNC. I think it's 7 threads per inch. I don't work in imperial, so I've got to write all this stuff down. So it's 1/8" UNC. 7 TPI, needs a 25 diameter drill size, which is going to be ideal for here. That's 24.5, so I'll just be able to clean that up and cut a thread in there. So we'll do this section first, and I'm going to make a Tommy bar through here so it's easy to grip and undo that. Alright, so what did I say? 7 TPI. That'll be alright. I'm going to change over my driver gear. I just barely see that scratch, so I'm just going to check that. Okay, I think I just did all of that threading and forgot to turn the camera on. But there it is there. That was a 7 TPI thread. The reason I did such a coarse thread was that when you unload the funnel or the hopper inside the blast cabinet, all the media is going to come out through this thread section. And if you've got a really fine thread and you try and put the cap back in there or the plug back in there, it's likely that it's going to get jammed up and score the thread. So at least with this big coarse thread we can sort of blow it out a bit and get it cleaned out fairly easily. Now I've just re-chamfered the 2 corners there, and I'll put this back in the chuck later and I'll drill a cross hole for a Tommy bar. I want to get the female thread cut in the aluminium casting and make sure that's all good before I go much further. So that's where my threaded plug needs to go, and the challenge now is to get this cleaned up on the end here and then cut the internal thread, and that's going to mean cutting a thread clearance inside. So I'm just going to get this cleaned up here. That's running out a bit more than I'd like, really. Let me see if I can get this running a bit more true. Okay, so what we need to do now is get that board out to 25. Now what I need to do inside here is get a groove cut so I can start my thread in the groove and then bring it out. Let that's the best I could come up with for a grooving tool. So I'm going to take this in 13 millimeters. And we're going to cut a shoulder. Okay. And can't see what I'm doing. Alright, so I've got a fairly deep groove in there now, and it should be wide enough. So that's going to be the starting point for our thread, and we're going to cut out away from that. Alright, this is a technique I saw Joe Piezinski using. He was demonstrating how to cut an internal thread to a hard stop. So what I've done is I've turned the boring bar tool backwards, and I'm running my lathe in reverse, and I've set up my lead screw so it's also running in reverse, and I've got a hard stop set on the bed. So what I can do is run my tool until it hits the hard stop, set my cross slide to 0, wind my feed on with the compound, and just start the lathe and start the lead screw, and it'll pull out, cutting the correct right hand thread as it goes. So let's try that, see how that works. Alright, so it's starting to cut the thread down, so it's just more of the same, and you've got to get your head around it. It's a little bit different to what you're used to, so I've got to stop and think very carefully before I do anything. So one of the things you got to do is you got to wind the tool back away from the circumference before you go into the hole, then reset your cross slide to 0. So that's a little bit different. I'm not having a good day, and my memory card filled up, so I missed the critical moment where I was about to show you how good this thread is. But I finished off using some cutting fluid just to give me a better finish on the internal thread, and you might say that's a bit wobbly, but I want to have some clearance there. I'm going to have a rubber washer for this to seal against, and that screws in there. Because it's such a coarse thread, I'm not bothered that it's a little bit wobbly to start with. It's going to make it easy to get in. And remember, this is going to fill up with grit, so that's okay. So what we're going to do now is flip this around. We're going to cut a thread on the other end, and that will be the one that secures against the door in the bottom of the hopper. This is the end that's going to fit into the bottom of the hopper door. So I need to cut a thread on this, and even though I normally work in metric for my North American friends, I'm going to make an exception. So I'm going to cut a 1.25" UNF thread, 12 TPI, and I've discovered that I can just get that same thread inside this hex nut, but I'll need to bore it out and re-thread that. So this is a one-time only thread. It's going to be done up tight on the bottom of the hopper door, and it's not going to move again after that, so I'm not too bothered about this being a finer thread. Just to save time, I already partly machined this just to get it cleaned up. So 2.22 millimeters or 87 thou off that. Right, so I'm going to put some thread relief there. It's not a lot, and I admire those people who do the quick withdrawal at the end of the threading pass and able to withdraw the tool while the machine's still running. That gets a bit scary for me. Okay, I'll set up for a 12 TPI thread. Got my threading tool in there, and I can use the half nut lever. That's basically why I've chosen to do this with imperial threads. My lathe has an imperial lead screw, so I can use the half nut lever to stop the threading pass, and that's a little bit more reassuring than trying to do it with the withdrawing the tool method, which I always find a bit scary. So let's just do our first pass, see what that looks like. Right, even there I don't have a lot of room to stop that thread, and I don't think I've got enough thread relief there, but who cares, let's live dangerously. I'll just put some dye on there so I can tell when I've got to the end of my threading pass. When most of that blue has disappeared and you just see a thin line at the top, you've pretty much got your thread to profile. Nearly there. I don't know if you noticed, but I didn't withdraw the tool enough when I brought it back. I left a little scratch mark on the way back. Sign of a rank amateur. That's about as far as I want to take that. So I'm going to machine this boss here now, and when you're doing a setup like this, I don't know, I always like to turn the spindle over by hand just to double check you're not going to have anything sort of clash and break or smash. I don't know how many times I've turned a lathe on with an odd setup like this and overlooked something, you know, like maybe the compound side's extending too far underneath the part. You just don't expect it to clash, and it does. So it's going to give this a light cut now. Let's mostly clean that up. Let's give it one more pass. Alright, so I can drill this in the lathe, and I don't know, it's just convenient for me to do it that way. So I'll get this laid out, just find a rough center. I suppose the good thing about this is none of these dimensions are really critical. I mean, the threads are, but other dimensions we can get away with a little bit of error. It's not a problem. Pretty hard to see there, but what you end up doing is with a pair of these Jenny calipers is you estimate the center, you scribe the line from one edge, flip it over, scribe it again, and if there's an error you just split the difference and that gives you the center. So I'm fairly confident I got that right. So we're going to set up now my drilling jig and we'll drill that through. This is my rig for doing this drilling operation. This is a really old AEG 2-speed drill with a metal gearbox, and I've seen some devices being used by home machinists and they generally rely on a cordless drill with a spindle bearing through here. If you can get one of these old drills, they're rugged enough and robust enough and they're rigid because they have the metal gearbox, and this is just a split clamp which has been machined out at the same height as my lathe spindle, and it just clamps down with a single Allen screw there. So let's go ahead and get this spot drilled and then we'll open it up. I'm going to put a 10mm metric thread in there. I know, mixing imperial and metric threads, I'm a rebel. Okay, it's got that thread started there. I'll finish it up by hand. This is the other configuration for the drill, and this fixture here is an aluminium casting with a split and a clamping bolt, and this one's set up at 90 degrees to the axis of the lathe, so I can drill a cross hole through this part and I know it's going to go through exactly on center. That's a handy little gadget. That should be a press fit for a 6mm steel bar or a brass bar, just as a Tommy bar. I'm going to go ahead and just finish machining this and part it off, and then that piece is done. Okay, that's close enough. That's going to be my 1¼ UNF nut, and we're going to cut a 12 TPI thread on the inside of that. that's a long way off being done, but I always second guess myself. Oh, look at that. That sloppy mark. Come on. Ah, it'll work. Good thing I checked that, eh? Hope Stefan's not watching. Alright, well that's slightly embarrassing, but there's going to be a rubber washer in this junction here, and that's going to allow it to seal against that door, and it's only got to get done up once, so I think I can get away with that. So we're pretty much done. I've continued that thread all the way through into the bore. This part's done. We've just got to make the thread and the fitting here, and make the most important part, which is the air bleed valve. Now I've got some stainless steel hex for doing that, and it's just got to have some ports in it and an adjustment screw, and that's it. So we're getting close. Be nice if that chip breaker did its job. I know I'm running that too slow. Let's try that. Okay, now I'm not sticking to any particular dimensions here. This has got a very, very simple function. It's just to allow a measured amount of air into the port. So if the commercially made ones are any guide, there are just a pair of holes drilled through across the center line or the center bore, and a threaded plug is wound down into that, so you can uncover one or both ports and you can vary the amount of opening. Okay, this is a letter drill, letter R. It's the closest thing I've got to an 8.75mm drill bit. And we're going to tap this M10 by 1.25, so it's a fairly, or is a metric fine thread. And it's just so that we get a little bit more fine adjustment on this. Probably not necessary. Alright, so I've taken that thread, or that hole for the thread, right down to that shoulder there. When I drill my two cross holes, I'll be able to block off both holes completely with the adjustment screw. And I'm just shooting in the dark here. I'm not sure what sizes these are meant to be. I guess we'll just sort of fine tune it as we go. it's not to depth, but I'll finish it off with a proper tap wrench later. Okay, well there are my two air inlets, and I'll need to make a threaded plug with some sort of a knurled knob on the end of that for the fine adjustment. And we'll get a thread on here and we're getting close. Well, this is the finished metering valve, and although if you check these out on eBay or on the website, you'll see that the whole aluminium casting and this device here are called a metering valve. In reality, I believe that the aluminium casting that you've already seen is just a way of attaching this device and letting it join the stream of media that goes from the hopper to the blast gun. And when I first saw this, I was expecting it to be some complicated piece of engineering with ball valves or reed valves or something. But now I believe that this is all it is basically. It's just a brass threaded plunger which progressively uncovers this pair of holes here. Now to make the plunger, it was just some scrap brass. I put an M12 by 1.25mm thread on this end, and I put a diamond knurl on this top part here. And I believe that unless you swap out the media and use a finer grit or a coarser grit, you're really going to adjust this once, and then after that you're not going to touch it. Now I've just set up the aluminium casting for doing the last machining operation on that. I'm going to use my CNC mill for that procedure. And sadly I'm going to have to finish this video here now because it's sort of gone over my self-imposed limit of half an hour for a video. So unfortunately you're going to have to join me on the next one to see if this little gadget's been successful. And having invested a lot of time to make this video, I'm more or less locked in to do the next one. And well, you just have to join me to see if I make a fool of myself and the whole thing's a failure. But even if it's a failure, we've learned something, haven't we? So join me on the next one and we'll have some fun with the CNC mill, and we'll put this thing through its paces and see whether it actually does what I think it's meant to do. Okay, check me out next time. See ya.